This is an audio recording for visually impaired students from the book Pradeep's Physical Chemistry, Volume 2 by Dr. S.C. Ketrapal. Thermodynamics 3. Work function, Helmholtz free energy and Gibbs function, Gibbs free energy. In addition to the various thermodynamic quantities like internal energy, work, heat, enthalpy, entropy, etc. discussed earlier, two more thermodynamic quantities used very frequently in the study of chemical thermodynamics are work function, also called Helmholtz free energy and Gibbs free energy, collectively called free energy functions. These are briefly described below. First, work function. This is usually denoted by the symbol A from the German word art, which means work, and is defined by the equation A is equals to U minus Ts, where U is the internal energy of the system, T is the temperature, and S is the entropy. Since U, T and S are the functions of the state of the system only and do not depend upon its previous history, therefore A also must be a state function. In order to understand the physical significance of the work function, consider an isothermal change taking place at temperature T. Then A1 is equals to U1 minus TS1 for the initial state and A2 is equal to U2 minus TS2 for the final state, where A1, U1 and S1 are respectively the values of work function, internal energy and entropy of the system in the initial state, and A2, U2 and S2 are the corresponding values in the final state. Therefore, increase in the function A accompanying the process will be given by A2 minus A1 is equals to U2 minus TS2 minus U1 minus TS2, which is equals to U2 minus U1 minus T common out from S2 minus S1, or delta A is equals to delta U minus T delta S, where delta U is equals to U2 minus U1 is the change in the internal energy of the system and delta S is equal to S2 minus S1 is the change in the entropy of the system. Now, according to the definition to entropy change, we know that delta S is equal to Q reversible upon T. Further, according to the first law of thermodynamics as applied to an isothermal reversible process, we have delta U is equal to Q reversible minus W max. Minus sign before W has been used to indicate that the work has been done by the system during the change under consideration. Putting the value of delta S and delta U from the equation 5th and 6th in the equation 4, we get minus delta A is equal to W max. Thus, for a process occurring in constant temperature, the decrease in the work function A is equal to the maximum work done by the system. In fact, it is for this reason that this thermodynamic quantity has been termed as work function, although at one time it is called Helmholtz free energy. Second, Gibbs function. This is usually denoted by G and is defined by the equation G is equals to H minus Ts, where H, T and S are the heat content, enthalpy, temperature and entropy of the system respectively. As before, since H, T and S are the function of the state, therefore G is also function of the state of the system only. Hence, the isothermal process occurring at temperature T, we can write G1 is equal to H1 minus TS1 for the initial state, G2 is equal to H2 minus TS2 for the final state. So that G2 minus G1 is equal to H2 minus TS1 is minus H1 minus TS1, which is delta G is equal to delta H minus T delta S, where delta G is equal to G2 minus G1 is the change in Gibbs free energy of the system, delta H is equal to H2 minus H1 is the enthalpy change of the system, and delta S is equal to S2 minus S1 is the entropy change of the system. The physical significance of Gibbs free energy may be obtained as follows. At constant temperature T, delta S is equal to Q reversible upon T, that is T delta S is equal to Q reversible. At constant pressure P, delta H is equal to delta U plus P delta V by definition of enthalpy change. Substituting the values of T delta S and delta H from equation 12 and 13 in equation 11, we get delta G is equal to delta U plus P delta V minus Q reversible, that is delta U minus Q reversible plus P delta V. Now, according to first law of thermodynamics, delta U is equal to Q reversible minus W max. Minus sign before W indicate that work is done by the system, or delta U minus Q reversible is equal to minus W max. Substituting these value of equation 14, we get delta G is equal to minus W max plus P delta V. Minus delta G is equal to W max minus P delta V. But P delta V is the work of expansion done by the system corresponding to the increase in volume delta V. Hence, W max minus P delta V stand for the maximum work other than the work of expansion. This is called the maximum net work available from the process. Hence, we conclude that for a process occurring at constant temperature and constant pressure, the decrease in Gibbs free energy is equal to the maximum net work obtainable from the process, that is the total work minus the pressure of volume work or work of expansion. It is because the change in G is a measure of the useful work done that G has been called as the free energy. It may be further mentioned here that it is customary to refer to Gibbs free energy simply as free energy. The designation Gibbs or Helmholtz is added only when necessary for clarity. Variation of Helmholtz function work function with temperature and volume. The work function is given by the equation A is equal to U minus Ts. Complete differentiation of this equation gives dA is equal to du minus Tds minus S dt. By definition of entropy change, we know that ds is equal to del q reversible upon T. Further, from the first law of thermodynamics, we have del q reversible is equal to du minus del w. And if the work is restricted to the work of expansion only, minus del w is equal to p dv. Putting this value in equation 4, we have del q reversible is equal to du plus p dv. Putting this value in equation 3, we get ds is equal to du plus p dv upon T, or tds is equal to du plus p dv. Putting this value in equation 2, we obtain dA is equal to minus p dv minus s dt. A. If temperature is kept constant, dt is equal to 0. Equation 8 takes the form del A upon del V at constant T is equal to minus P. If volume is kept constant, dV is equal to 0, equation 8 becomes del A upon del T at constant volume is equal to minus S. Equation 9 and 10 give the variation of work function with temperature and volume. The change in work function for a complete process under isothermal condition can be calculated as follows. For an infinitesimal change under isothermal condition, equation 9 may be written as dA at constant temperature is equal to minus P dV. For a complete process under isothermal condition, when the volume changes from V1 to V2, we will have del A at constant T is equal to integration V1 to V2 P dV. Putting PV is equal to nRT, that is P is equal to nRT upon V for n moles of an ideal gas, we get del A at constant temperature is equal to minus nRT log V2 upon V1. This is same result as derived earlier in equation 7, page 113. Variation of Gibbs function or free energy with temperature and pressure. The free energy is given by the equation G is equal to H minus Ts by definition of enthalpy. H is equal to U plus PV. Putting this value in equation 1, we get G is equal to U plus PV minus Ts. Complete differentiation of the equation gives Tds is equal to du plus Pdv. Substituting these value in equation 4, we obtain dg is equal to Vdp minus Sdt. This is an important expression which gives the change in free energy with change in pressure and change in pressure in a reversible process. Equation 6 is called total differential equation. A. If temperature is kept constant, dt is equal to 0. Equation 6 takes the form dg at constant T is equal to Vdp at constant T. B. If pressure is kept constant, dp is equal to 0. Equation 6 become dg at constant P is equal to minus S dt at constant P. Equation 8 and 9 give the variation of free energy with pressure and temperature. The change in free energy for a complete process under isothermal conditions can be calculated as follows. For an infinitesimal change under isothermal condition, equation 7 may be written as dg at constant temperature is equal to Vdp. For a complete process under isothermal condition, when the process pressure changes from P1 to P2, we will have del G at constant T integration P1 to P2 Vdp. Putting PV is equal to nRT, that is V is equal to nRT upon P for n moles of an ideal gas, we get nRT log P2 upon P1. Further, for an isothermal process, P1 V1 is equal to P2 V2 or P2 upon P1 is equal to V1 upon V2. Substituting these values in equation 12, we get del G at constant temperature is equal to nRT log P2 upon P1 or nRT log V1 upon V2. This is the same expression as equation 13, page 115 for change in work function. Thus, del G at constant temperature is equal to del A at constant temperature. This appeared to be a contradiction from the result discussed earlier in section 2.14. However, it may be understood clearly that the equality hold good for an ideal gas but not in general. Criteria for feasibility or spontaneity of a process. As already discussed in section 2.6 and 2.7, the net entropy change for the combined system and the surrounding can be taken as a criteria for the feasibility or the spontaneity of a process. This result arrived at were: first, if del S of system plus del S of surrounding is greater than 0, the process is irreversible, that is, it is spontaneous or feasible. Second, if del S system plus del S surrounding is equal to 0, the process is reversible, that is, the system is in equilibrium. The above two results may be combined and put in the form del S system plus del S surrounding is equal to greater than 0, where the sign greater than refers to an irreversible process, that is spontaneous process, and sign equal to for a reversible process, that is for a state equilibrium. The above criteria, however, requires knowledge of both del S system and del S surrounding, which is not convenient. Hence, a number of other criteria which require the knowledge of the change in some thermodynamic quantity of the system only are preferred. This may be derived as follows. For an infinitesimal process, the above criteria may be written as ds system plus ds surrounding is greater than equal to 0, where the sign greater than stands for a reversible process and sign equal to for the reversible process. If the surrounding lose heat, Q reversibility and isothermally at the temperature T, which may be absorbed by the system reversibly or irreversibly, then ds surrounding is equal to minus del Q reversible upon T. Further, according to the first law of thermodynamics, del Q reversible is equal to du plus P dV. Substituting the value in equation 3, we get del ds surrounding is equal to minus du plus P dV upon T. Substituting the value in equation 2, we get ds system minus du plus P dV upon T is greater than equal to 0. Or TdS is greater than equal to du plus P dV, where ds stands for the entropy change of the system and the subscript system has been omitted. Equation 6 is the basic equation which leads to a number of criteria for predicting the feasibility of a process. In this equation, the sign equal to stands for the reversible process and the sign greater than for the irreversible process. In terms of entropy change of the system, if the internal energy and the volume of the system are kept constant, du is equal to 0 and dv is equal to 0, then from equation 6 we have ds at constant u and v is greater than equal to 0, where the sign equal to for the reversible process and sign greater than for the irreversible process. The subscript u and v indicate the constancy of these properties. Second, in terms of internal energy change of the system, if the entropy and volume of the system are kept constant, ds is equal to 0 and dv is equal to 0, then equation 6 becomes 0 is greater than equal to du at constant s and v, or du at constant s and s or v is less than equal to 0, where the sign equal to stand for reversible process and sign less than for the irreversible process. This implies that if a process under constant condition of entropy and volume is accompanied by a decrease of internal energy, the process is irreversible. If no change of internal energy takes place, the process is reversible. Third, in terms of enthalpy change of the system, by definition of enthalpy H, we know that H is equal to U plus PV. Complete differentiation of this equation gives dH is equal to du plus PdV plus VdP. Putting this value in equation 6, we get TdS is greater than equal to dH minus VdP. If entropy and pressure of the system are kept constant, dH at constant S and P is less than equal to 0, where the sign equal to refers to reversible process and sign less than refers to irreversible process. Fourth, in terms of change in work function of the system. By definition, work function A is given by A is equal to U minus Ts. Differentiating this equation completely, we get Tds is equal to du minus sdt minus dA. Putting this value in equation 6, we get SDT plus dA is less than equal to minus PdV. If temperature and volume of the system are kept constant, dt is equal to 0 and dV is equal to 0, so that we have dA at constant T and V is less than equal to 0, whereas usual sign equal to is for the reversible process and sign less than for irreversible process. Fifth, in terms of free energy change of the system, by definition, free energy is given by G is equal to H minus Ts. Further, H is equal to U plus PV. Therefore, G is equal to U plus PV minus Ts. Complete differentiation of this equation gives du plus PdV is equal to dG minus VdP plus TdS plus SDT. Putting this value in equation 6, we get dG minus VdP plus SDT is less than equal to 0. If pressure and temperature of the system are kept constant, dP is equal to 0 and dt is equal to 0, so that we obtain dG at constant P and T is less than equal to 0. Whereas before, the sign equal to refers to the reversible process and the sign less than refers to irreversible process. The criteria in terms of free energy change is most significant because most of the process take place at constant temperature and pressure. This criteria implies that first, if dG at constant P and T is less than 0, the process is irreversible, that is, it is feasible. Second, if dG at constant P and T is equal to 0, the process is reversible, that is, system is in equilibrium. Third, if dG at constant P and T is greater than 0, the process does not occur, that is, it is not feasible. Limitations of the criteria for spontaneity. Not doubt, the various criteria discussed above are helpful in predicting the spontaneity of a process, but they do not tell anything about the following. First, the extent to which the reaction takes place. Second, the rate at which the reaction proceeds. Third, the mechanism by which the reaction proceeds. Advantage of free energy criteria over entropy change. An important advantage of free energy criteria over the entropy criteria lies in fact that the former requires free energy change of the system only at constant P and T and is not concerned with what is happening to the surrounding, whereas the latter, that is entropy change criteria, requires the total entropy change of the system and the surrounding, that is for the process to the spontaneous del S total is equal to del S surrounding plus del S system must increase. Gibbs-Helmholtz equation. The Gibbs free energy G is given by the equation G is equal to H minus Ts. Hence, for an isothermal process, we can write G1 is equal to H1 minus Ts1 for the initial state, G2 is equal to H2 minus Ts2 for the final state. Subtracting equation 2 from equation 3, we get del G is equal to del H minus T del S, where del G is equal to G2 minus G1 is the change in free energy of the system, del G is equal to H2 minus H1 is the change in enthalpy of the system, and del S is equal to S2 minus S1 is the entropy change of the system. Taking up equation 1 again and putting H is equal to U plus PV, we get G is equal to U plus PV minus Ts. Differentiating the equation completely, we get TdS is equal to du plus PdV. Substituting this value in equation 6, we get dG is equal to VdP minus SDT. If pressure is kept constant, dP is equal to 0, so that we have dG at constant pressure is equal to minus SDT at constant pressure. Therefore, for the initial state, dG1 upon del T at constant pressure is equal to minus S1. For the final state, del G2 upon del T at constant pressure is equal to minus S2. Subtracting equation 8 from 9, we get S2 plus S1 is equal to minus S2 minus S1 is equal to minus del S. Or it may be written as del G plus del H plus T into curl del G upon curl T at constant pressure. This is the most common form of Gibbs-Helmholtz equation, starting with the expression for the work function, that is A is equal to U minus Ts, proceeding exactly in a similar manner as above. The following analogous expression can be derived. Del A is equal to del U plus T curl del A upon del T at constant volume. This is another form of Gibbs-Helmholtz equation. Further, sometimes Gibbs-Helmholtz equation is put still in another form, which is derived from equation 11 as follows. Dividing equation 11 throughout by T square, we get del G upon T square is equal to del H upon T square plus 1 upon T curl del G upon curl T at constant pressure, or curl del G by curl T upon curl T at constant pressure is equal to minus del H upon T square. It may be noted that all forms of Gibbs-Helmholtz equation involve quantities like del G and del H, or del A and del U, which are state function and do not depend upon the path followed. Hence, Gibbs-Helmholtz equation is a general equation applicable to reversible as well as irreversible process. Applications of Gibbs-Helmholtz equation. One of the applications of Gibbs-Helmholtz equation expression 11 is that knowing the free energy change at any two different temperatures, the enthalpy change accompanying the process can be calculated. However, the most important application of the Gibbs-Helmholtz equation is in the study of galvanic cells, which is briefly explained below. When a redox reaction is allowed to take place in a single beaker, heat is evolved. Earlier, it was believed that when the same reaction is allowed to take place in an electrochemical cell, the electrical energy produced was equivalent to the half evolved. However, later on it was found that in a number of cases, the electrical energy produced is not equivalent to the heat evolved. This was explained by Gibbs and Helmholtz by stating that the electrical energy produced was equal to the decrease in the free energy accompanying the cell reaction. They pointed out that if n is the number of electrons given out by one of the electrodes or taken up other electrode, then the quantity of electrically produced is equal to Nf Faradays, where F is equal to 1 Faraday is equal to 96,500 coulombs. If E is the EMF of the cell, then electrical energy produced by the cell is equal to NFE. Therefore, decrease in free energy minus del G is equal to NFE. Substituting this value in the Gibbs-Helmholtz equation, we get NFE is equal to minus del H plus TNF into curl E upon curl T at constant pressure. Thus, knowing the temperature coefficient of the EMF of the cell, that is curl E upon curl T at constant pressure, del H can be calculated. If E is known or vice versa, evidently the electrical energy produced is equal to the heat evolved only when curl E upon curl T at constant pressure is 0. Nernst heat theorem. W. Nernst 1906 made a detailed study about the variation of enthalpy change and free energy change of a system with decrease of temperature. The result thus obtained is called Nernst heat theorem and is briefly described below. According to Gibbs-Helmholtz equation, del G is equal to del H plus T into curl del G upon curl T at constant pressure. From the equation, it is evident that at the absolute zero, that is when T is equal to 0, del G is equal to del H. However, Nernst observed that as the temperature is lower towards absolute zero, the value of curl del G upon curl T described and then approaches zero asymptotically. This means that del G and del H are not only equal at absolute zero, but the values approach each other asymptotically in the vicinity of this temperature. This result is known as Nernst heat theorem. Mathematically, it may be expressed as limit t tends to 0 d del G upon dt is equal to limit t tends to 0 d into del H upon dt is equal to 0. Graphically, the result may be represented as shown in figure 3.1. In figure 3.1, del G has been shown as greater than del H at temperature away from absolute zero. However, the reverse is also possible because curl uh, dg del g upon curl t can be both positive or negative. But we know curl del g upon curl t at constant p is equal to minus del s, and curl del h upon curl t at constant p is equal to del c at constant p. Combining these results with equation 1, we get limit t tends to 0, del s is equal to 0, and limit t tends to 0, del c at constant p is equal to 0. Since gases do not exist at the absolute zero, this means the heat theorem is not applicable to gases. Similarly, it has been found to be inapplicable to liquids also. Thus, Nernst heat theorem is applicable to solid only. Third law of thermodynamics. The result of Nernst heat theorem led to enunciate a generalization which has been called as the third law of thermodynamics. In other words, the third law of thermodynamics follows the result of Nernst heat theorem as briefly explained below. According to Nernst heat theorem, del Cp approach 0 at 0K. This implies that at 0K the heat capacities of the reactant and product become equal. If it seems most probable that at 0K all substances have the same heat capacity. On applying quantum theory to the heat capacity of solid, it is found that heat capacity of solid tend towards 0 at 0K. Thus, Nernst heat theorem leads to following result. Limit t tends to 0, C at constant P is equal to 0. Also, the Nernst theorem limit t tends to 0, del S is equal to 0, proceeding exactly in the same way as above, it may concluded that all solid have the same entropy at absolute 0 of temperature, and it tends towards 0 at absolute 0 of temperature. That is, limit t tends to 0, S is equal to 0. This generalization is known as third law of thermodynamics. It may be stated as under: the entropy of all perfectly crystalline solid may be taken as 0 at the absolute 0 temperature. In a broader sense, the law is usually stated as follows: every substance has finite positive entropy, but at the absolute 0 of temperature, the entropy may become 0, and in fact, it does become 0 in case of perfectly crystalline solid. Like the first and the second law, this law is also generalization based upon experience, and there is no direct proof for this law. However, the law has been verified in a number of ways, and there is no doubt about the validity of the law. It is important to note that the third law of thermodynamics does not state that entropies are 0 at T is equal to 0. It merely states that all perfectly crystalline solid have the same entropy at T is equal to 0. Choosing a common value as 0 is only a matter of convenience. Importance of third law: evaluation of absolute entropies. The importance of third law lies in the fact that it helps in the calculation of the absolute entropies of element or chemical compound at an desired temperature. This may be illustrated as follows. The infinitesimal entropy change is given by ds is equal to curl q upon t, but Cp is equal to curl q upon dt, so that curl q is equal to Cp dt. Substituting this value in equation 1, we have ds is equal to Cp dt upon T. Hence, the entropy change of a substance when its temperature changes from absolute 0 to the temperature T will be obtained from the equation St minus S0 is equal to integration 0 to T at Cp dt upon T, where S0 is the entropy of the substance at absolute 0 and St is the entropy of the substance at temperature T. Now, according to third law of thermodynamics, S0 is equal to 0. Therefore, St is equal to integration 0 to T Cp d ln T. Thus, the entropy S of the substance at temperature T can be calculated from the measurement of heat capacities at a number of temperatures between 0K to T degree K. The integral in equation 3 can be evaluated by plotting Cp versus ln T, that is 2.303 log T, or Cp upon T versus T, and then measuring the area under the curve between T is equal to 0 to T dot A. A typical A typical plot is shown in figure 3.2. Thus, the evaluation of entropy requires the measurement of heat capacities at different temperature down to 0 K. However, a problem arises with the measurement of heat capacity at low temperature. For example, in the plot given in figure 3.2 above, the heat capacity along the curve BC are experimental values. The point B corresponding to the lowest temperature up to which the experimental values can be determined accurately. To get the complete area under the curve from T to 0K, extrapolation of the curve is done as shown by the portion BA of the curve. The value corresponding to extrapolated portion is usually found by applying Debye third power law for the heat capacity of solid at low temperature. Cp is equal to A T cube, where A is an empirical constant. If B corresponds to temperature T1, that is the lowest temperature up to which heat capacity can be measured experimentally. C corresponds to temperature T, that is the temperature at which entropy is to be determined, and remembering that A corresponds to 0K, integral given in equation 3 can be split into two parts as follows. St is equal to integrate 0 to T1 Cp upon T dt plus integration T1 to T Cp upon T dt. Hence, equation 5 becomes St is equal to At1 cube upon 3 plus integration T1 to T Cp upon T dt. Further, as Cp is equal to At cube, therefore At1 cube upon 3 plus 1 upon 3 Cp is equal to 1 upon 3 Cp at T1. This means that the entropy change from 0K to T1, that is St1, is equal to 1/3 of the values of Cp at T1. Hence, equation 5 can be simplified further to the form St is equal to 1 upon 3 Cp at T1 and integration T1 to T Cp upon T dt. It is important to remember that the calculation as described above are applicable only to a solid involving no polymorphic change, that is a change from one crystalline form to another between 0 degree to T degree Kelvin. If some polymorphic change is involved in this range, the entropy of transition is equal to del TRH upon TTR, where del TRH is the molar heat transition and TTR is the transition temperature, will have to be included in the values calculated above. For liquids and gaseous substances, the total absolute entropy of the substance at the given temperature will be the sum of all entropy changes which the substance has to undergo in order to reach the particular state starting from the crystalline solid at absolute zero. Thus, if a substance is gaseous at 1 atm pressure and 25 degrees Celsius, the entropy of the gas at 25 degrees Celsius will be sum of the following entropies involved at different stages. First, the entropy of heating the crystalline solid from T is equal to 0 to T is equal to Tf, the melting point or fusion temperature. Second, the entropy of fusion or fission is equal to del Fh upon Tf, where del Fh is latent heat of melting or fusion. Third, the entropy of heating the liquid from Tf to Tb, the boiling point. Fourth, the entropy of vaporization, del Vh upon Tb, where del Vh is latent heat of vaporization. Fifth, the entropy of heating the gas from Tb to 25 degrees Celsius, that is 298 Kelvin. Thus, the complete expression for the calculation of entropy at temperature T may be written as St is equal to integration 0 to Tf Cp d log T plus del Fh upon Tf plus integration Tf to Tb Cp d log T plus del Vh upon Tb plus integration Tb to T Cp d log T. A. If the substance is solid at temperature T, only first term is to be taken with Tf is equal to T. B. If the substance is liquid at temperature T, the first three terms are to be taken with Tb is equal to T. C. If the substance is gaseous, full equation is to be used. If the solid involves a polymorphic transition, another term is equal to del TRH upon TTR has to be included in the above expression as already explained. Further, the first integral should be made up to two parts as given by equation 5, 6 and 7. The various entropy changes that occur when the temperature of a substance rises from absolute zero may be represented diagrammatically as follows. The calculation of standard molar entropy of nitrogen gas at 25 degrees Celsius is illustrated with the data given below. It may be noted that the heat capacity is very low at low temperatures. Hence, errors that arise due to debris extrapolation are very small and almost negligible. Test of the third law of thermodynamics. First, by calculation of equilibrium constant. The equilibrium constant K is related to standard free energy change del G naught according to the equation minus del G naught is equal to RT ln K. The standard free energy change is related to the standard enthalpy change del H naught and standard entropy change del S naught according to the equation del G naught is equal to del H naught minus T del S naught. Putting the experimental value of del H naught and calculated value of del S naught using the absolute values of entropies obtained from the third law of thermodynamics and applying the relation del S naught is equal to sum of S naught products minus sum of del S naught reactant. Del G naught can be calculated for a reaction. Putting the value of del G naught in equation 1, the equilibrium constant K can be calculated. It is found that for a number of reactions, the value of equilibrium constant as calculated above comes out to be in close agreement with the experimental value. Second, by comparing with entropies calculated from statistical mechanics, the absolute entropies calculated on the basis of the third law are found to be complete agreement with those calculated using statistical mechanics. Third, by proving that different allotropic forms of a substance have equal entropies at absolute zero. Orthorhombic sulfur S alpha changes into monoclinic sulfur S beta at the transition temperature of 369 Kelvin. The enthalpy of transition del HTR is found to be minus 402 joule per mole. Hence, molar entropy of transition will be given by del TRS is equal to S alpha minus S beta is equal to minus 1.09 joule per Kelvin per mole. The individual entropies of the two forms can also be calculated by measuring their heat capacity from T is equal to 0 to T is equal to 369 Kelvin. It is found that S alpha is equal to S naught beta plus 37 joule per Kelvin per mole. S beta is equal to S0 beta plus 38 joule per Kelvin per mole. Hence, the transition temperature del TRS is equal to S0 alpha minus S0 beta minus 1 joule per Kelvin per mole. Comparing equation third and fourth, we get S0 is alpha is minus S0 beta is equal to 0. That is S0 alpha is equal to S0 beta. The elements in perfectly crystalline form are arbitrarily ascribed a value of 0 for the entropy of absolute 0. Then all perfectly crystalline compound will also have 0 entropy at 0 K, keeping in mind the definition of the entropy of formation of a compound. Residual entropy. As explained above, entropies can be determined by applying third law of thermodynamics. These can also be calculated from statistical mechanics or from spectroscopy data. It is found that in most of the cases, the agreement between the third law of entropies and those calculated from statistical mechanics is very fair. However, in some cases, the experimental value as found from third law is found to be less than the calculated value. For example, standard entropies found from third law and calculated from statistical mechanics for CO and N2O are given below. The lower values of third law entropies are explained on the basis that at T is equal to 0 Kelvin, the crystals of these substances are not perfect. That is, there is some disorder present in the solid even at T is equal to 0 K. The entropy which the crystal of a substance has at T is equal to 0 K is called the residual entropy. Origin of residual entropy. To understand the origin of residual entropy, let us consider a crystal made up of AB molecule where A and B are similar atoms so that the molecule has very small electric dipole moment. These molecules can adopt different orientations such as AB, 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 AB or AB, BA, BA, AB. These arrangements or many other random arrangements that the molecule can adopt have very little difference of energy. Thus, there is a residual disorder and hence there is residual entropy at 0 K. Calculation of residual entropy. Residual entropy can be calculated by applying Boltzmann formula S is equal to K log W, where W represents the number of possible orientation of the molecule that are equal probable, that is, have nearly the same energy, and hence W is called thermodynamic probability and K is Boltzmann constant. A few examples are given below. First, residual entropy of CO. Suppose a sample consists of n molecules of CO. Now, as each molecule can have two orientations that are equally probable, that is CO, CO, OC, CO, OC, OC. Therefore, same energy can be achieved in 2n different ways. That is, W is equal to 2 raised to power n. Hence, S is equal to K log 2 raised to power n is equal to Kn log 2. If 1 mole of the sample is taken, Kn is equal to R, then S is equal to 5.85 joule per Kelvin per mole. Second, residual entropy of FClO3. FClO3 molecule can have 4 possible orientations with nearly same energy. Hence, residual entropy is S is equal to R log 4, which is equals to 11.5 joule per Kelvin per mole. In general, if a molecule can adopt p possible orientation at t is equal to 0, which have nearly the same energy, the residual molar entropy will be Sr is equal to R log p. Thank you.